So good morning, everyone. Let's start. My name is Ziye Yang from Intel. My topic today is accelerator Ceph block service via SPDK. And today we will have the following agenda. I will first have a brief introduction of SPDK, and then I will introduce the methodology about how to use SPDK to accelerate the block service built on Ceph. Then we will talk about some SPDK support in bluestore, in Ceph open source project. Then we will have a conclusion. So first is what is SPDK? The full name is Storage Performance Development Kit. It is a user space library, which is already open sourced in SPDK.io, and it is BSD licensed. And the foundation of SPDK library, the idea is a user space a synchronized port mode driver. And the foundation driver in SPDK is the user space port mode NVMe driver. It has the better performance, which can achieve the similar performance with Linux kernel, but using less CPU cores. And why we need to develop SPDK software? The reason is that we know that the hardware becomes very fast. It will have high IOPS and low latency. Compared from the left to right, you can see that from HDD SATA-based NAND SSD, NVMe NAND SSD, and the latest 3DX point based NVMe SSD or 3DX point based NVDIMM. The storage device becomes fast and fast, and the current issue is blocked by the software IO stack. We know that previously, if the hardware device is very slow, then the improvement of system software IO stack may not be quite useful. But currently, the situation changes. The software IO stack becomes a bottleneck, and the long IO stack, which may include the kernel IO stack, it may have lots of locks. There will be lots of resource contentions among the kernel threads. But we know that kernel will also improve its performance. But currently, we would like to provide SPDK, which is a user space library, which can shorten the IO stack. As you know, SPDK is not a general IO stack. It may not be fit to all kinds of usage scenarios. But we are confident that SPDK can be used in several use cases, like the block service demo. We can improve that, which can include the iSCSI target and many over fabrics target. And this diagram shows the architecture of SPDK. You may be familiar with this during the previous 3 days SDC conference. Let me have a brief introduction on this. Actually, SPDK's library can be divided into 3 layers. The foundation, as I said, is the drivers layer. We have the NVMe device user space drivers and their IoT drivers. And in the storage service layer, we have the similar block device abstraction like the idea in the kernel. And we also have the blob-fs, blob-store, which is a very simple non-POSIX file system, or it is not a file system. It can only support limited operations on object. And the blob-store has some encapsulation which can be integrated with RocksDB to provide the database engine service. And in the upon layer, we can see that we support various of storage protocols. Currently, the listed protocol are all block-based. We can support iSCSI target. We can also have vhost SCSI target and vhost block target, which can be used to accelerate the Vert I/O in the virtual machines. And we also have the latest NVMe over Fabrics target based on SPDK's all different components. Naturally, we may have some path-finding work on object interface. And this page shows some performance data compared with existing Linux kernel solutions. For example, the per-core performance of user space ME driver is 10x better than Linux kernel. I would emphasize the improvement is based on per core. Since if you have lots of CPUs, you can always achieve the physical limitation of the NVMe devices. And we also have the other data. Actually, I will not talk it in this talk. And this page shows some websites of SPDK. We open sourced the SPDK project in GitHub, and we have some features, discussions, and ongoing work, which is demonstrated on Trello. Everyone can register an account and add yourself into SPDK group and post your ideas to improve SPDK or post some requirements. And we also have our code review in GitHub, which is also open to public. And we also have the regular day-to-day discussions on IOC SPDK. And the last one is the homepage of SPDK, which includes all the useful informations, including the document, and also some programming guides. And this page shows a promotion. We will have the SPDK hackathon in Chandler, Phoenix this November. Welcome to everyone to join this event. So the previous section introduced SPDK library, and this section we will introduce how to use SPDK to accelerate the block service exported by Ceph. Actually, we think that we can leverage SPDK to improve the block service on Ceph in 2 dimensions. The one dimension is that we can improve the block service daemon outside Ceph. It means that currently we may use Linux IO target, TGT, or other iSCSI target service to put in front of Ceph as the iSCSI gateway. But definitely we can use SPDK iSCSI target. The reason SPDK iSCSI target is better than the the existing solution, we will talk more details in later. And the second is that we can do some optimization inside Ceph, especially in OSD. For example, in OSD's in bluestore, we can leverage SPDK's user space and mini driver to drive their IO operations to many devices instead of using a kernel and many driver. And the second, we can also bring some ideas in SPDK BroFS, bluestore to enhance the BroFS or bluestore in Ceph. The last one is that we can also improve the network. Actually, we know that in Ceph, we already have the DBDK async messenger, which can be used together with SPDK. Then we can improve both the network I/O and also the disk I/O. But definitely for the network I/O optimization, will not be talked in my talk today. And this page shows the diagram on how to use SPDK to accelerate the block service. We know in the diagram you can see it is very simple. We just replace the existing iSCSI target or many over fabric targets with SPDK's iSCSI target and many over fabric's target. And also we may have the cache module included in this block service demo, which is utilized to improve the performance. And in the other dimension, we can improve the bluestore, like the description in the diagram. We can firstly leverage SPDK's many driver. Also, we can bring some ideas in SPDK to enhance BroFS. For example, for the memory management in OSD, we can use the DBDK's memory management methods in SPDK and improve the performance on memory side. And this page just demonstrates the performance comparison between SPDK iSCSI target and the Linux I/O target. In this comparison, our SPDK iSCSI target still use the Linux kernel TCP/IP stack, but previously we have libUNS. But since the temporary stop of libUNS, we just compare the SPDK iSCSI target through the kernel TCP/IP stack. We can see from the diagram, it seems that the performance of SPDK is a little better than Linux IO kernel. But you can see from the diagram, to achieve such performance, Linux IO kernel use 32 CPU cores, but SPDK only use 21. If we calculate the per core performance, SPDK is almost 2x efficient than Linux kernel. And the major improvements is caused by the following reasons. Our SPDK iSCSI target use non-blocking TCP sockets, and we have our own APP core framework. It means that we can ping iSCSI targets, iSCSI connections in dedicated CPU cores. Thus, each CPU core can handle its own iSCSI connections. That means it will not have the resource contention on memory on the other resources. And also we have the user space and many driver, which elements the the efforts by kernel I/O stack, such as the context switch or the system core overhead. And the next page will show a detailed usage case, which is provided by SPDK Company in PRC, which is shown in SPDK meetup last year. This diagram shows the customer's iSCSI target service built on Ceph. You can say that the client will use the multipass, and it will connect the iSCSI gateway. And finally, the iSCSI initiator will connect the iSCSI target. And the iSCSI target can use the librd to connect or to consume the block service provided by the OSD. Actually, for the RBD things, you can use the kernel RBD. Or actually, in SPDK, we have encapsulation of librados and librd. We will provide the Ceph RBD BDEV devices in SPDK. So it means that you will not need to use the kernel RBD module. And this page shows some system configuration and also some configuration of Ceph. And this page shows the read performance comparison. We can see that in this diagram, we have the string. String means that the client will use the FIO to do the jobs on one image, two images, or three images. And the left diagram, left one shows the core configuration. For example, both SPDK iSCSI and TGT uses one CPU core, and another one is the two CPU core configuration. And we can see that for the 4KB read and read performance, SPDK iSCSI target is better than the existing TGT solution. Majorly, it can average. We can improve the performance more than 30 to 40%. And the reason why the performance improvement is not close to the previous compression on the DAS storage is that you know that for the DAS storage we have the user space and mini driver. We have this acceleration, but for the Ceph it is a distributed file system, so this advantage will be eliminated. And this page also shows the write performance comparison. It has a similar result, so I will skip it. And the next page shows some proposals or opportunities to better leveraging SPDK in Ceph. We know currently for SPDK, if you use SPDK mini driver, one mini SSD can only be used one OSDs. And definitely we can improve this situation with some multi-process mass storages demonstrated in SPDK project. For example, we can include the SPDK MNE over Fabric target, and this target can provide virtual MNE devices to different OSDs. Definitely for the protocol support. Currently, we only have the RDMA based solutions in SPDK MNE over Fabric target, but we may soon have the TCP/IP acceleration or protocol support, and then we may also have the IPC protocol support. We may use the vhost protocol. It means that different OSDs can use their IPC to connect their SPDK many over file detector in the same host. Thus, we can make different OSDs to consume the same many device if the users want to do this. And the other solutions maybe currently for the many device solution. Many device means actually the file name to leverage SPDK many driver. Currently, it does not have the read-write cache when you using SPDK many driver. Currently, I reviewed some code of the kernel device solution. It definitely uses two FDs. One is for direct I/O. The second is for buffered I/O. Then it can leverage the kernel page cache. Thus, sometimes for the performance, the kernel solutions may be a little better than SPDK. So definitely we may include this cache buffer strategy when using SPDK. And the second is for the zero copy. Currently, when you enable SPDK to start the OSDs, you still use the normal memory allocations through glibcs. We hope that we can do some work to directly use the DBK or SPDK provided memory management strategy. Then we can eliminate the unnecessary memory copy when doing the read-write IOs to the many device. And the next page will show the current SPDK support in Ceph bluestore. If you browse the source code of Ceph, we can see that during the last 10 months, yes, we have update SPDK from the 1.2 version to the following 3 versions. It means that every time when SPDK is announced a new version, we will soon update it in Ceph. And also, we are continue some stability maintains in Ceph when using SPDK. Especially those days, we are submitting the related patches in Ceph and try to make enabling SPDK in default. It means that when you use CMake and type make it, we can build a default Ceph OSD with SPDK support. And this page shows the potential SPDK support for Ceph in the future. Actually, we are still doing the following three type of works. The first is continuous stability maintains. We will try to make SPDK work in Ceph in different or in the new versions, and we will continue the performance enhancement, also the bug fix work. And the third one is that we will also do some new feature development and make it much better. Definitely, we hope that we can work in these three scopes with the customers. Oh, that's summary. In my today's talk, I first introduced the SPDK, then introduced how to use SPDK to improve the block service in Ceph. Definitely, SPDK is already proved to be useful to explore the capability of many SSDs in many situations, like the iSCSI target, many over fabric target, vHost target. But currently, truly speaking, if we want to have product level quality in Ceph, we are still need extra development efforts to make them much better. So here I would like to cover some actions. If you are interested, you can pay some time to participate in the SPDK community. Also, we are welcome to leverage SPDK for Ceph optimizations. If you have some questions, you can directly contact your SPDK development team for some collaboration and help. You can post those questions in SPDK mailing list or in IRC or directly drop some emails to us. So that's my total presentation. Thank you.